So coming to the generative AI again, so that is at our hands to generate synthetic data. So data is always in scarce. Suppose a new disease has come like COVID-19. So initially we don't have much of the images with our doctors. We need to train our deep learning algorithms in this sense. Only few hundreds of images are available of just X-ray affected by COVID-19. So what we can do with those 100 images, we can generate thousands of images using generative adversarial networks. So that is what is the interesting explanation and coding part we are going to see now. These are all the GAN generated human faces, and in medical applications, this shows a CT image of a human skull. This is original, and these are all generated by the GANs. Okay. So much as we cannot observe any much difference between these and these. So the success of GANs will be properly generating the normal data and the abnormal data. And here comes another interesting example. This is collaborative imaging. This forgot the name. Interdisciplinary image generation. That is, they train the GANs with the MRI and CT image. And further, if you give MRI image only, they will generate the GANs will generate the corresponding CT. That's what we need not go for CT imaging itself. Initially, the GANs are generated with MRI image and the CT image of the same person and the same anatomy. And the GAN gets trained with multiple images like that. Then we can go for an MRI image alone. So the GANs are capable of generating the CT image. So it's not like a magic. So papers are published like that. So if you look at this paper, I forgot the name, but cross-modality medical image estimation. So cross-modality medical image estimation, you have two modalities, CT and MRI, where if you train the GANs, generative adversarial networks with CT and MRI of the same person and same anatomy for several hundreds. Newly, if you give the CT alone, MRI image will be generated by the. So these are very, very interesting things that is going to be trendy in the future, not right now also. Right now it is happening little. So in the future, GANs will be there.
Their voice is not visible, not clear, sir.
Yeah. Just now the Bluetooth connection got disconnected.
Okay, sir.
Sir, Raja sir.
Yes, sir.
So nice, sir. You had a great
please
session,
tell me,
but I couldn't be in the session for complete duration.
Okay,
It was with a different assignment.
Are you able to hear me now?
Yeah.
Now it is clear, sir.
Shall I proceed?
Yes, sir.
Because my Bluetooth is not connected, but still you are hearing the photo in this software. Okay, whatever. So as I told you, this is called as a cross-modality image generation by using GANs. So that's what is a GAN? Let us see. Generative adversarial networks is a deep learning architecture that consists of two neural networks in competition against each other. So there are two neural networks that is called as a generator and the discriminator. They work in competition with each other. That is in the sense. What happens in the sense? You have two things. Generator takes the input from a latent noise variable. So here you give some noise variable as input to the generator. So the generator will be generating some random noisy image. So it is not at all relevant to the original image which you want to generate. Some noise is being generated and that is given to the discriminator. So at one point, if you see, the discriminator will get the images from real samples and also from the generator. So what we start doing initially is, we train the discriminator properly. That is properly in the sense, the original image when we are giving, we call it as a label 1. So we train the discriminator by saying the original image is original itself. But later what we do, the generator's image is also told as 1. So we are trying to fool the discriminator. So what the discriminator will do after a certain period of time, instead of learning the fake inputs, what it will do now, the discriminator will try to twist the truth. Twisting the truth in the sense, what it will do now, the generator and the discriminator will act in collaboration and start generating the images that are similar to the real images. That is what is the interesting part with the GANs. So I think it is little pretty confusing. Okay. So I also got confused even after implementing the code also. Now also I have to study once again to get to the concept again. So that is what is happening in the generative adversarial network. We have a generator and discriminator. The role of the generator as it implies, it is used to generate some fake data. Fake data is generated by triggered by some latent noise variables. So some noise variables are given as the input in the sense. It will generate fake images of same size. Okay. So initially the images will be totally different compared to the original image. Suppose I fundus images are my original targets in the sense. This real data sample will only have that real eye images, whereas for the same size, some noise is being generated here, and that is given to the discriminator. Initially, the discriminator is trained properly, in the sense whatever real data that flows here, that is trained with the label 1. So as we have the supervised learning everywhere. What is the supervised learning as we know? The last thing is nothing but the label. For whatever features extracted, the last column is nothing but the label. Is here in the GANs, the supervised learning is done by taking the real images as 1 and fake images as 0. So the discriminator starts learning all these, and after that the fake images generated are also labeled as 1. So then what happens? The discriminator's loss function becomes enormously large. So what always artificial neural networks tend to do? Artificial neural networks tend to reduce the loss function. So after the generator and discriminator training and evaluation, we have a combined model phase also. In the combined model phase, what is happening? Both the generator and discriminator will act in combination, so that what will do, the discriminator will twist the truth. Twisting the truth in the sense, for the label it will start generating the data. So at a point of time after several iterations, the data that is being generated by the generator will start resembling the real data. That is what is a generative adversarial network, to put in a theoretical perspective. Generator generates fake samples of data, maybe it may be an image, audio, etc., tries to fool the discriminator. The discriminator, on the other hand, tries to distinguish between the real and the fake samples. The ultimate aim of the discriminator is to properly detect whether it is a real data or fake data. The generator and discriminator run in competition with each other in the training phase. That is, during the training phase, they act as opposition. Okay. At one point of time, they act as a combined model and then make the fake data similar to the original data to reduce the reduce the loss of the discrimination. So that is what is happening. The steps are repeated several times, and in this, the generator and discriminator get better and better in the respective jobs after each. So that is what. So when you go for a GAN, generative adversarial network, the loss function is very important. So as I told you, this binary cross entropy loss, where YA is a Y true, there is a ground truth, and the probability of YA is a Y predicted. There is a prediction from the artificial neural network. Inspired by this binary cross entropy model, here also we have the loss function. So what is the loss function? What is the discriminator's output to X? What is X? X is the sample data, that is the original data. Discriminator's output to the original data, followed by discriminator's output to the fake data. So X is the original data and Z is the synthetic data. We have designed the loss function. We have designed in the sense it is already implemented in GAN. So generator's output, for the generator's output, what is the output of the discriminator? So two models are acting in series. The output of the generator for which we get the discriminator. And here the constants are nothing but the data that is taken from the real data and the samples from original data and synthetic. So this is the loss function of it. GAN. So we'll see the implementation of GAN also.
Maybe student மாத்தி theory ஒரு ஆளு lab ஒரு ஆளு verify.
So this is these are the original images which are taken, so which we are generate synthetically by using GANs. After the implementation of GAN, whatever synthetic data that is generated, but you have successfully generated GANs anyway. Maybe by changing the loss function or by increasing the number of iterations, at one point we can become successful in generating synthetic images by using the GANs. So what is the coding perspective, as I already told you? So like we saw in the MNIST example, we need to import the corresponding libraries, okay, TensorFlow. And in fact, the layers also we are going. We are connecting to our Google Drive. So these are the lines in which we connect to our Google Drive. In my Google Drive, I have a folder called images. So to that it will. Okay. So here we have some lines of code to pre-process the images. This is ultimately image reprocessing operations, like reading the images and resizing the images. And then we have extrain. Extrain is nothing but the training data. Okay. As usual, as I told in the previous example, if I take as numpy dot shape of extrain, it will show how many images are taken. 101 images are taken, each of size 28 by 20. For my own interest, I'm seeing the input. Suppose we are designing an amplifier experiment. Okay. Application of sine wave, you will see. Before that, what is the original input is properly coming or not. So likewise, we will observe the actual input also. What are the inputs that are being taken? And then again some pre-processing operations. So we are taking some variables n, h, w, explain dot shape and the sense. It will take the number of rows and number of columns and n is the number of images. N is the number of images. H, w. So when you go for the coding aspects of deep learning architecture, it is always important to have in memory the shapes and sizes. Okay. How many images you have taken? 101 images you have taken. Each of size 28 by 28. So those things are taken in these variables. The D is a single variable where we multiply 20 into 20. So sometime when we are training the CNN, we are not taking it as a matrix. We are taking it as an array itself, and then we are training the CNN. So D is taken 28 by 28, which is nothing but 784. And now if you put the numpy dot shape of extrain, it is 101 images, each of size 784. So that is what we call it as this images are being flattened. And regarding the implementation of GANs, I have given another slide. There is nothing but how this particular code is being taken to reality is, first we have to define a generator and run the generator. First we have to define and run the generator. Then we have to define and train the combined model. So that is what the sequence of operation happens here. So for comparison between the sizes and compatibility of sizes, they are given in this order. Whereas in actual implementation, we will define the generator and define the combined model. These two things we will do first, and then we will run the generator, and then we will train the combined model, and we will see the output of the combined model. So these are the steps worthy remembering to know how this particular code is being working. First, we have to define a generator and a discriminator. So generator plus discriminator is called as the combined model. First, we have to define. What is by defining? Defining is nothing but what are the different layers that are there in the particular CNN. So it is worthy remembering that both this generator and the discriminator or generator plus discriminator combined model, all are nothing but CNNs, convolutional neural networks. So we are going to take them. And what we are importantly interested to see about their sizes now. The input we are giving to the generator is of size 100. That is, a 100 length array is given as noise input. So based on that noise input, the generator will generate an output image of size none, 784. So in deep learning algorithms, we get this none in the sense that will be useful for later adaptation. Later adaptation in the sense that size can take anything in the corresponding operations. 784. When you use the same entity again, that can be taken to any value. That is the advantage of taking this 784. So otherwise, when you see in so many codings, always there is a none comma, one comma, two, something like that. So that is useful for that. So coming back to the discussion, you have a generator, you have a discriminator. So what you do in the generator, by giving an input noise of size 100, you generate a fake image of size 784. That 784 is nothing but a flattened image of size, actual size 28 by 28. Then you run the generator. When you run the generator, the actual input noise we are giving is 32. What is the 32? 32 is nothing but so only when you understand these numerical values, you can understand the code. So all these, what is the 3200? Why he is saying this? All these are meaningless. Instead of 100, if you give 200, what is going to happen? So if you are tired of learning this code, understanding of the code is difficult. So that's why I'm telling you. So when you run the generator, you give a input noise of size 32, 100. 32, 100. So if you want to understand the code, you may take a note also. Otherwise, it's going to be a difficult task to understand the code. So 32 is a batch size. So batch size in the sense, if you have some 100 images also, they are trained and validated in batches. So in a batch, we are going to give 32 images and we are going to generate 32 images. That is what is of 32. And the 32 noise sequences we are going to give as an input. So you please understand one thing. This generator is going to generate fake images by taking noise sequences or noise vectors. That is what we are doing here. So 32 batches of 100 values, all these are noises. So when you run this, what will be the output of the generator in the sense? They give 32 images of size 784. They are nothing but fake images. They are not original images. Then after running the generator, we have to define a combined model. So combined with the generator and the discriminator. You need to have a deep thought why this is one instead of seven. Why this is one in the sense, what is the discriminator ultimately going to say? The discriminator is not ultimately going to produce any image. The discriminator is going to give only a decision whether it is a synthetic image or original image. So our logic is if it is an original image, the output will be equal to 1. If it is a synthetic image, the output is going to be 0. That is why when we have this sizes, understanding these sizes are very important when you want to implement a deep learning model. 100 comma 1. Okay. And after that, training the combined model by giving 32 batches of noise sequences of length 100, you are going to generate 32 decisions. So this is less important. So in between what is there now, the combined models output you will take it as the GAN generator. That's what we have done in the coding part. GAN generated images are freely available internet. Freely it is available. Freely it is available only with online data sets. But later we developed the code to take the images from specified folders and generate the images of our own interest. So that is what is the minor task I have done to implement this GAN. So whatever inputs I am giving, so based on that, the GANs are able to generate. So let us dive in coding. So little bit I have told. We are at the level of building the generator and the discriminator. As I already told you, this generator is nothing but a CNN. So data dimension 100 in the sense, you are giving a noise sequence of size 100 as input to the. Whatever may be in between happening is not our interest. Finally, what is the size of the input and size of the output? That is where we will be safe without getting any errors. We go for a deep learning model. Here you can give 256 instead of 256, you can give 2056 also. Not going to affect coding. Whereas the input and output sizes should be taken. But anyhow, what are all there in between? There are dense layers. As I already told you, the dense layers are nothing but the fully connected layers where the actual learning will be happening. So here the convolution layers are not given in the sense it means that there is no feature extraction here. The data is learned rawly. That is what is the meaning that after input you have dense layer now. The raw data is being learned by the CM. That is what here. And after that building the generator, you go for building the discriminator. For discriminator, what is the input size and output size? It is none, comma, 100. So here we can infer the different layers of your CNN. And finally, the discriminator summary is it takes the fake images generated by your generator and it is given as input to the discriminator. Matching it. This is it. Okay. The generators, fake generated images are given to the discriminator. That is what is accomplished here at this point of time. Still, we are not running the model. We are only defining the model. Defining the model in the sense we are going to say what should be the different layers that should be available in the discriminator, generator, and the discriminator. So after defining the model, we build the model, build the discriminator, and then compile the model. Okay. So discriminator is the model that is built for a discriminator CNN, and this is it. Okay. So when you look at the shapes, what we can see now, those fake images that are being generated by this generator as given as input to the discriminator. And already I told importantly, that is, when you look at the output sizes, it is very important to understand. The output of the combined layer will be always equal to 1. Why? Because it is always a decision. Okay. Discriminator is not going to produce any image. Generator is only going to produce the image. And the original data set is also going to give the image. The discriminator is going to tell whether it is a 1, that is, if it is taken from the original data set, or if it is a 0, if it is taken from the fake data set, that is a generator output. Okay. So the output should be either 0 or 1. That is why sizes are standing as 1. And after that, what we have to do now? Create an input to represent the noise sample from latent space. So latent dimension in the sense we are given 100. So we need to generate a vector of size 100 with which the noisy images will be generated. So generator of Z we are giving, and the fake prediction is equal to discriminator of the image. So discriminators output to the generator. In fact, this is the line where we have this particular entity. You know, like D of X is the original input given to the discriminator. Z is the fake data given to the generator. And the fake data, fake image generated by the generator is given to the discriminator. In fact, that is the line here. It is going to give the generator of Z, the output is given to the discriminator. This is what we have as a fake prediction. After defining the generator and discriminator, we have to define the combined model also. What is the combined model? This model is little different from whatever model we have seen so far. This is different. This is also a model. Discriminator is also a model. Build discriminator is also a model. So these are all defined by us. These models are defined by us. Whereas with capital M, if you type, that is an inbuilt function in deep learning. It is an inbuilt function in this era of memory. If you type with a small m, it is different. If you type with a capital M, that means it is a default model taking the corresponding input as Z and the fake prediction as output. Okay. So we are just saying what we are saying now, sir. What the output also we are declaring on the right hand side. You may get confused. Output will be always there on the right hand side. But we are defining a model. This model will take a noise source as input, but it will produce an output called fake prediction. That's what we are saying. And compiling the model. That's why I keep on telling them we have not run the model. We are just building the model. When we build the model, the syntax is like model followed by input comma. So what is the combined model? Ultimately, one thing I will be very much interested to know, the combined model's output is also equal to 1. That means the combined model is also going to say whether we have generated, whether the generator has combined model has taken a normal image or fake image. Those things are. And this is next important module that is taken here, which is called that every run of your combined model to showcase your image and save your image. What is done here now? The images are somewhat rescaled. Here we call it sample underscore images of. Sample underscore images is not an inbuilt Python command. That is what we are declaring here. Define sample underscore images means for every epoch, the particular images that are generated in batches should be saved to your folder, and also they should be plotted. And also some rescaling operation is done here. And next, coming to the important part called training the discriminator and training the combined. So as you can see here, extrain. What is extrain? Extrain is the actual data we are taking. When you go back to the code also, we can infer that the extrain is nothing but the actual data samples we take here. That is nothing but the extrain of index. So index we are generating some random. So all those things, we go for micro analysis of the code. It is tough to complete this. And after that, we generate some noise, as we have seen here. Some noise is given as input to the combined model. That is what is given here to generate the fake images. So here two things we need to infer. The real images are taken and the fake images are generated. Okay. And the discriminator is trained with both the real images and also with the fake images. Okay. So we are giving the label for real images as 1. We are giving the fake images label as 0s. Okay. And from that we are calculating the discriminator loss and the discriminator accuracy. And then we are averaging the loss and the very pretty things there. So first initially we are training the discriminator with real images and fake images with the labels as ones and the, then training the combined model. That's what when I gave the explanation, first I told the discriminator is first genuinely trained by giving the original samples label as 1 and the fake samples label as 0. Then after some time, this is called as training the combined model. Training the combined model in the sense, in the last function we have this term E of G of Z. That is for the say fake samples, sorry, for the noise, the generator is generating fake images that is given by G of Z. And for the fake images, what is the decision of the discriminator? That is E of G of Z. This is the combined model. And the combined model is acting here. So the combined model, what is done now? Again, noise is being called. For the combined model, you are training on batches with the noise as input, the ones as the. So this is what is very, very important in a GAN, which we will not do in any other machine learning operation. Usually, the original image is given as 0 and the fake images are given as, sorry, original image is given as 1 and the fake images are given as 0. But here we are twisting the truth. We are just faking the discriminator by saying noise inputs as 1. So what will happen automatically after some time? The loss of the combined model will be very high. It keeps on being high with the noisy input, fake images taking the label as 1. After some time, the combined model will twist the truth. It will generate the data that are similar to original data so that the lie is being made as a truth. It is the, instead of generating noise, it will start generating the original images so that the loss becomes reduced. So then the mapping will be done to real images, sorry, synthetic images that resemble the real images and the label will be equal to. Then in such a situation, the loss will become getting. That is the concept behind your generative adversarial. So finally, we are showing the loss of the generator and discriminator. So combined model loss is very high and discriminator loss is very less. Okay, we are not Initially, when you are training the discriminator separately, you are giving the proper inputs. That's why the discriminator loss is very less. But combined model less keeps on oscillating. Why? Because you are faking the combined model. You are giving the noise input and drilling it as equal to drilling input, so that the loss gets fluctuated. As you can see, the model has not compiled properly. So once it compiles properly, the GAN outputs, whatever I am able to generate, will be very much resembling the original images. So as far as concerned, you have designed a very much baseline model of your generative adversarial network, which can generate synthetic data that resembles the original data. Finally, when you execute this particular lines, whatever the images that are being generated will be saved in your local environment. You can download that and see what are all the GAN generated. In fact, we trained the GAN on some COVID chest X-ray images also. We got some better outputs. So these are the original COVID chest X-ray images. Whereas these are the GAN generated. So I know there is still a long way to go, because here the loss functions are the conventional loss functions we are using. Binary cross entropy we are using, which is nothing but this one. Instead, we have to manually implement this GAN based loss so that the generated images will be somewhat better. I think that is it for this session. Then these are the references. Anything else I want to say now? We have some work. I told some tabular data set. So we have generated tabular GANs also. It's a UG project we have done some couple of years ago. So the National Health Repository of Medicine, it gives a COVID-19 data set, as I told. We have generated, sorry, the data set consists of 1604 entities. Using tabular GANs, our students generated around 1000. So the burden of proof is on us. So when we generate synthetic data using GANs, it is our burden to prove that the synthetic data, whatever we generated, is as statistically significant as the original. So the burden of proof is there. So when you read the papers that work on GANs, you can see that some papers they generate synthetic images using GAN, and they will end up saying that when you augment the data, augmentation of data is done using the GAN generated images, then my accuracy. Likewise, some papers will claim. Whereas here, what they have implemented now, progressively growing GAN. So this is a progressively growing GAN, which is little complicated in architecture. Whereas baseline for anything is this one. That too, we have not taken the, we have not taken the data sets like MNIST. So in fact, the online data set for MNIST is only downloaded, and we kept on changing the code for from our folders. We have to take the input, and we will be able to download the generated images. It will be useful for publications. Then I told about loss functions. I just wanted to show that how can you generate your own loss functions. If possible, we'll see in some other way. Okay, that's it, sir. My presentation is over. Thank you all for your attention. Do you have any queries? About it?
Dear participants, if you have any kind of queries, you can raise, please. Rajesh sir,
Yes, sir.
it was a great session. Almost 1.5 hours without a break. You have taken a
Hello?
nice session, sir.
Sorry, excuse me.
I think someone has opened the mic to throw some question.
I think Saidulu, any question, please?
Yes, sir.
Yes, you can go ahead, please.
Good afternoon, sir. Saidulu.
Yeah, good afternoon.
How does a CNN differ from a fully connected? How does a CNN differ from a fully connected neural network?
Yeah, neural network consists of limited number of layers that connects to machine learning. So, from my understanding, this is
Finally, your mentors.
it's not a textbook matter I am telling, but from our understanding, if we connect, the artificial neural networks are more connected to machine learning, having less number of layers. And if you operate with more number of images, thousands and millions, thousands and 10,000s of images. So that connects to deep learning that has to be done with the convolutional neural network. Importantly, you have something called as a convolutional layer in C. Whereas artificial neural network is little different, where you have a very standard type of input data. Features are extracted by domain-specific methods. For example, you want to extract some type of features from images. Now you will extract like energy, entropy, or wavelet-based values you can extract, and those numbers will be fed as input to the neural networks. And directly, immediately after the feature extraction, the classification or learning or weight learning will happen. Whereas in deep learning, we have convolution layers explicitly for this. So one more perspective we can say is domain-specific feature extraction is more in machine learning, whereas in deep learning, same convolution layers, same type of activation functions, but it is successful to any domain. That is what is the advantage of your this images.